In last lecture, we had seen one problem on design of one-way slab. In that, we have note down all the design steps, and accordingly that those design steps we have designed the one-way slab. Now we will see second problem on design slab. In that, the problem statement is that a 3-meter wide passage supported on 230 thick side walls. See, a 3-meter wide passage. We have to design a passage of 3-meter wide. So it is supported on 230 thick side walls. Carries a superimposed load of 375 kilonewton per meter square, including floor finish. This superimposed load is nothing but it is the sum of live load and floor finish. That is, directly you have given an addition of live load and floor finish, and that is equal to 375 kilonewton per meter square. Then we have to design the suitable slab using M20 concrete, that is FCK is 20 Newton per mm square, and Fe 415 steel, that is Fy is 415 Newton per mm square. Use 8 mm diameter bars. See, in the problem it is advised to use 8 mm diameter bars and 6 mm diameter bars as distribution steel. Take MF modification factor as 1.4. Apply the checks for maximum area of reinforcement. See, here one extra step we have to add here for check for maximum area of reinforcement, minimum area of reinforcement, and spacing. Do not apply checks for shear and bond. Generally, for one-way slab, check for shear and check for bond is not required. Keep in mind. Sketch the cross section. Use effective cover as 20 mm. So we'll start with the problem. Again, here is the cross section of slab. See the effective depth, effective cover, overall depth, layer span, effective span. These are the important notations, and accordingly we are going to design all the things. Okay. Then next, in that problem, following is the given data. That is, shorter span L is equal to 3 meter. Wall width, that is support width, is 230 mm. Superimposed load using floor finish, that is floor finish is equal to live load, is 3.75 kilonewton per meter square. Here FF is equal to LL. It is not FF is equal to LL. It is the addition sum, that is floor finish plus live load is equal to 3.75 kilonewton per meter square. Then modification factor MF is equal to 1.4. Effective cover is given as 20 mm. Material M20 and Fe 415, that is FCQ 20 mm and Fy 415 Newton per mm square. Then we have to design one-way simply supported slab. Since it is a passage, for passage we have to design a one-way slab. Then step first, calculation of effective depth, that is assumed, that is D assumed is equal to span upon 20 into mm. That is span is given as 3 meter, that is 3 into 10 to 3 in mm upon 20 into mm. Mm is given as 1.4, that is 107.14 mm. Say 110 mm. We have to increase the depth. As depth increases, the bending moment reduces. So we are going to increase this depth by 3 to 2 mm. That is, say 110 mm, or you can take as 107.14 mm, no problem. Assuming 20 mm effective cover, since here cover is given as 20 mm, we don't want to assume that cover. We will take 20 mm as effective cover. Therefore, overall depth D is equal to 110 plus 20, that is effective depth plus effective cover, that is overall depth is equal to 130 mm. Then next is step 2, that is calculation of effective span. That is, effective span is calculated, that is L effective layer span plus effective cover. effective, not effective core, it is effective depth. The effective depth is 130 mm, that is 3000 mm plus 130 mm, that is 3130 mm, that is 3.13 meter. Then load calculation. Then in that first load is dead load, and this dead load or weight of the slab is 25 kilonewton per meter cube to 1 meter width of the slab we have to consider, and D is the overall depth, that is 0.130 meter, width in 1 meter and 25 kilonewton, that is 3.25 kilonewton per meter. Then superimposed load, that is addition of floor finish and live load, that is given as 3.75 kilonewton per meter square into 1, that is 1 meter width we have considered, that is total weight is in kilonewton per meter, that is 3.75 kilonewton per meter. Then total load per meter width is the addition of dead load plus superimposed load, that is superimposed load is nothing but it is the addition of live load plus floor finish. The total load is 7 kilonewton per meter. Therefore factored load is equal to 1.5 into W, that is 1.5 into 7, that is 10.5 kilonewton per meter. See, same steps are adopted as in problem number 1 for problem number 2. So there is no change in the design method. So you have to consider any problem and put in this format, then you will get the design. This is the simply supported beam carrying UDL load of 12.86 kilonewton per meter, that is factored load, and the effective span is 3.13 meter. For this effective span we have to calculate the bending moment, and that bending moment is equal to WL square by 8, that is W 10.5 into 3.13 square divided by 8, that is 12.86 kilonewton meter, that is 12.86 into 86 Newton mm. This is the ultimate bending moment acting on the slab, and this bending moment we have to consider for the calculation of required depth, because depth is the only criteria to reduce the bending moment. So it is very important. So fifth step is the required depth for bending moment, that is for Fe415 MU limiting value is 0.138 FCK BD square. Therefore MU limiting is equal to MU. Equating all these, we can calculate the depth required as D is equal to 68.26 mm. This is the required depth for given bending moment, and actually we are assuming that depth very large than the required, so we are safe for the depth. The next step is we have assumed the depth as 110 mm and required depth is 68.26 mm. So we have provided more depth than required, so it's okay. Therefore provide D required is equal to 110 mm. Now the overall depth D is equal to 110 plus 20 mm is the effective cover, that is 130 mm. This is the first design for the slab. Then next step is the calculation of main steel using 8 mm diameter bars. Since in problem we have given 8 mm diameter bars as main steel, then main steel is calculated by using this formula. AST main is equal to 0.5 FCK upon Fy into bracket 1 minus under root of 1 minus 4.6 MU upon FCK BD square, bracket complete, B into D. Put all the values of FCK and Fy, width, depth, and the AST main is calculated as 346.63 mm. This is the main steel. Then spacing for this main steel, that is check for minimum steel for highly yield stress bars, that is AST minimum. This is given by IS code, that is AST minimum should not be less than 0.12% gross area, that is 0.12% of gross area means B into capital D, that is B width is 1000 into overall depth is 130, that is 156 mm square is the minimum steel requirement. And for maximum steel, it is maximum steel is provided 4%, that minimum is 0.12% of gross area, and maximum steel we have to provide is 4% of gross area, that is 0.04 into B into capital D, that is 2000 mm square. And since as maximum steel required maximum steel we have to provide is 5000 2000 mm square is largely greater than actual AST, and it is again greater than AST minimum. So the steel provided by us is correct. Then spacing for main steel of 8 mm diameter bars, again using the formula width into area of one bar divided by total main AST, that is width 1000, pi by 4 into d square is the area of one steel bar, d diameter of bar is 8, that is 8 square, that is spacing required is 145 mm center to center. So this spacing should not be greater than 3d, that is 3 into 110, that is 330 mm. It should not be greater than 330. We have provided 145. It's okay, and it should not be greater than 300 mm. So it is again okay. Less than 300 or 330 mm, 145 mm is less. So provide this spacing. So provide main steel 8 mm diameter at a spacing of 140 mm center to center along shorter span. Then next step is calculation of distribution steel. This distribution steel is taken as 0.12% of gross area, but see here, actually we have to using 6 mm diameter bars, and it is a plain steel. We have to take it as 0.15% of gross area. So you take here 0.15. I had taken here 0.12%. It is not correct, because to remember this formula to calculate distribution steel, while using the distribution steel you have to going to use 6 mm diameter bars. So you are using a mild steel. For that mild steel it is 0.15% of gross area. So calculate this area. This is the homework for you. Then spacing required for this distribution steel is B into area of one bar. Here you are using 6 mm diameter bars, so that spacing is near about 181.24 mm, say 180 mm center to center. And finally the summary of design, that is we have provided depth of slab as 130 mm, main steel as 8 mm at 120 mm center to center, distribution steel as 6 mm at 180 mm center to center. Okay, like this we have to solve all such problems, and if any problem regarding this you can directly phone me. I will solve all the doubts regarding this design of one way slab. In next lecture again different type of one way slab problem we will see, and we will stop here. Thank you.
So advance में